close packed structures. In this we try to understand the packing in the crystalline solids. Now before moving into the packing of the crystalline solids, we need to understand one basic term which is called coordination number. It is the nearest number of particles that present around a particular particle, or it is the number of particles with which a particular particle is in direct contact. So if we have a particle like this and it is in contact with almost like here 5 more particles, 1, 2, 3, 4, 5. So we will say the coordination number of this central particle is 5. So nearest neighbors, the number of nearest neighbors is called coordination number, or the number of particles with which a particular particle is in direct contact is called coordination number. So whenever we will study the packing and we will move on into the different stages of packing, definitely we will give emphasis on this term and we will try to find out what are the coordination numbers at each stages these crystalline solids are having. So let us start the packing. The packing in the crystalline solid starts from first one-dimensional system. In one-dimensional system, the particles will be, we will be taking of course marbles or small balls of the same size, and we will try them to arrange with one another so that we can find out what all are the possible the arrangements or the structures we can have in which they can be arranged. That could give us exactly the possibly all types of possible existing crystal systems. So in one-dimensional system, since the particles are of one type, they can be arranged, actually they are arranged in a single line. It's like this. So they are arranged in one line, and in this you can find that each particle is in contact with 2 more particles. So what we find is that the coordination number at this stage is 2. Now, as the packing moves to the 2-dimensional system, this packing, which is actually was in one line in case of one-dimensional, in 2-dimensional system, this can be of 2 types. Of course, the parameter is how they are arranged. The one type is like this, in which particles are arranged one below the other. It's like this. When particles are arranged like this, one below the other, and they are actually, when you join the centers of these particles, you find that they are forming a square. We call this type of packing is called square close packing, SCP. Square close packing, SCP. It's a 2-dimensional packing, and in this you can easily make out that each particle is in contact with 1, 2, 3, 4 more particles. Not these ones which are lying along the diagonal, because diagonal ones are having this distance. So the coordination number in this case of square close packing of 2-dimensional is 4. Also, what you need to understand at this stage only is that these unoccupied spaces, these ones, are called interstitial spaces, or they are also called voids. These are the unoccupied spaces called voids or interstitial spaces. So this is one of the pattern we can have in which the particles can be arranged in 2-dimensional system. You can make out easily now these voids or interstitial spaces are of very large size. So when you arrange these particles like this and you just disturb them, you will find that they will be arranged in the second type of option, in which what we find is the particles are arranged one below the other. It's like this. I can draw it again for you in a much better way. The second type of packing in 2-dimensional system, same. is almost as like this, in which the particles are arranged one below the other. It's almost as like this. Now in this, if we join the center of the particles which are surrounding a particular particle, we find that these particles are arranged in hexagonal manner. Therefore, this packing is called two-dimensional hexagonal close packing. It's called HCP. HCP. And in this, this center particle is in contact with 6 more particles. So coordination number in this case is 6, and you can make out in these cases, these are the small interstitial spaces of voids we have, which are much smaller than the square close packing. So therefore what we find is, out of the two types of packing, square close SCP and HCP, HCP is more economical because here more of the volume is occupied and very less interstitial, small interstitial spaces are left. So this is what we have HCP packing. Now let us see how these two types of packing changes to a three-dimensional system when they are actually, we put layer of the other particles above this layer. Now let us see how the two-dimensional packing is changed to a three-dimensional packing. For a three-dimensional packing, we will be putting up another layer, the layer of the particles above this first layer of particles, which are arranged in two ways, the square close packing or hexagonal close packing. So we know the first layer of particles in two-dimensional system is arranged in two possible ways, SCP, HCP. Now for making them to move into the three-dimensional system, we'll put the layer of the another layer above this first layer of the particles, and then we have to see how we can place this. Now in case of square close packing, we already know the particles are arranged one below the other. They are like this. Now in this case, when we move to the three-dimensional system, the second layer of particles is placed just exactly above this first layer of particles. So it's like this. So black color is indicating the second layer, the red color is indicating the first layer, and you can see that the second layer is exactly above the first layer. That is why this type of packing in three-dimensional is called AAA type of packing. AAA means what? The first, second, third and subsequent layers, all of these layers are resembling with each other. They are exactly one above the other. There is no difference. And this type of packing, which is obtained from a square close packing, two-dimensional square close packing, is called AAA type of packing. And this type of packing leads to the formation of primitive type of unit cell or SCC unit cell. So this type of packing forms SCC unit cell. SCC unit cell. And what will be the coordination number of the particles in this case? I will tell you later on, because I will show it to you with the help of a diagram. So this is what the three-dimensional structure we can get out of SCP, and this is what is the basic aim of studying the packing, is that how we get the different types of unit cells and how when the particles are arranged in different patterns. This is how we get the SCC type of unit cell. When the square close packing type of particles arranged are having what? The same type of layers are repeated one above the other, we get SCC type of unit cells. Let us see what happens in case of HCP. Now let us see how the HCP type of two-dimensional packing is changed to a three-dimensional packing. Now in HCP type of packing, what we find is the particles are arranged one below the other two. It's like this. Now in these cases, what we find is the particles are already very closely packed. That's why the topic is close packed structures. and the voids or the interstitial spaces in these are very small, though they are of two types. Most of these are, all of these are actually triangular in shape like this. So, and they all are of the same size. We call these ones as A, which are pointing upward, and the one which are pointing downward, we call them B. Now, this is what is the first layer you have, which is drawn with the red pen. Let us see how we put the second layer. Let's take the second layer of the particles is actually placed above the void A. So when we are placing the particles of the second layer, which are drawn with the black colored marker, above these voids A, which are pointing upward like this, what we find is, let me cover them so that this becomes very clear. So what we find is, this red colored marker are showing first layer, this black colored marker are showing, this particles are showing the second layer. So at the stage of the first layer, we were having two types of voids, A and B, but both were of the same type, so that any one of those can be covered. But whereas in the case of the second layer, now on the second layer what we find is there are two types of voids available. Let me draw them with the green color marker. These are the one which are available, which were actually left out while putting up the second layer, called B voids. And a new type of void is formed by the second layer particles. It's called C type of void. So on the second layer, we are having two types of voids. B, the same one which were left uncovered while forming the second layer, and the C, the new type of void which are formed by the second layer particles. Now, therefore, while putting up the third layer, we have two options. The two options are to cover B voids or to cover C voids. Now, suppose we are covering let us take the first case that we are covering the C voids. I'm again drawing it with green marker. C is this void. If this is covered, you can easily make out that this green colored ball is exactly above this first layer particle, which is drawn with the red color marker. So what we find is this green and red are lying one above the other. So it means what? The first layer resembles the third layer. And that's why when the C void is covered, the type of packing which we get is called AB type of packing. It's called AB means what? The first layer resembles third, second with fourth, and then this is repeated and so on. So it's called AB type of packing. And then the other option, if we cover the B voids like these one, we can easily make out that even this third layer is not resembling with your the first, second layer. So this third layer is very different from your first and second layer, and all these three layers are different. That's why this B type of packing leads to the formation of ABC type of packing, in which the first three layers are different. The first layer resembles the fourth, second with fifth, and so on. So this type of packing leads to the formation of ABC type of packing. This leads to the formation of AB type of packing. So this is what the different type of packings we have. Now let us summarize the packing. In one dimensional, we know the particles are arranged just one after the other. The coordination number was 2. When this packing one dimensional is changed to two dimensional, we know we have two types of patterns: SCP packing, square closed packing, and two-dimensional hexagonal closed packing. When this two-dimensional system is changed to three-dimensional, we know SCP type of packing leads to the formation of AAA type of packing. This forms SCC unit cell. That's most important. Now, we know HCP. HCP in three-dimensional forms two types of packing. One is called AB type of packing. This AB type of packing is also called three-dimensional hexagonal close packing, HCP. And we know the other type, it was ABC type of packing, which is also, this one is also called cubic close packing, CCP. So we have HCP turning into two types of packing in three-dimensional system. HCP, three-dimensional HCP, which is also called AB type of packing, and three-dimensional ABC, which is also called cubic close packing or CCP packing. So these are the two types of packing we have in case from which is obtained from HCP, and we have one type of packing AA, which is obtained from SCC. So altogether we have three types described: AAA, AB, and ABC. Now we know from AB AA type we have got the SCC type of unit cell. We need to understand what type of unit cells we are obtaining or are getting from these type of packing. In case of ABC packing, this type of packing gives you FCC unit cell, which you can easily see in your diagrams, three-dimensional diagrams from the books, that this type of packing leads to the formation of FCC type of unit cell. Now, this type of AB types of packing leads to the formation of three-dimensional hexagonal unit cell. So this forms hexagonal unit cell, this forms face-centered unit cell. So these are the different types of unit cells which we get out of these type of packing. Now let us understand how we determine the coordination number of a particle in a three-dimensional system. Let us take SCC unit cells. You can see now here a crystal lattice has been drawn, which is having 8 unit cells, 4 at the bottom and 4 at the top, and each unit cell is your simple cubic unit cell, or it is a primitive unit cell in which particles are only present at the corners. Let us take this central particle, this one, which is being shared with these all 8 unit cells. If we take this one, it is in contact with how many other particles? 1, which is the back 1, front 2, left 3, right 4, 5 top and 6 bottom. So what we find is that the coordination number in case of SCC is always 6. Similarly, we can find out the coordination numbers in the other cases, like, let me rub out this one. In case of any body-centered unit cell, the particle which is there at the center of this unit cell will be in contact with all those 4 particles which are lying above it and all these 4 which are lying below it. So it is in contact with how many other particles? 8. So remember, in case of BCC, the coordination number is 8. And the coordination number, similarly, you can find out in case of FCC is also 12. In case of hexagonal close packing unit cell, which we got from AB type of packing, remember, the coordination number is also 12. So what the biggest thing we can make out is, since we know the Z, let me draw that with the other pen, you can easily remember then, That as we know, the Z in case of FCC is 4 and the coordination number of the hexagonal unit cell is also 12, so its Z will also be 4. That means both of these types of unit cell will be having same number of particles per unit cell, 4, 4. So this is very valuable information which everybody must know. Now let us study the types of voids we have.